going to explain the difference between accuracy and precision. We're first going to talk about the definitions between the two words, and you should be able to tell, based on a set of data, whether it's highly accurate or good precision based on the definitions. So what is the difference between accuracy and precision? So high accuracy is the average is very close to the true value. So accuracy is all about how it compares to the actual value of that substance. So for instance, the density of water is 1 gram per centimeters cubed. Now if you were to do a lab and you found the density to be 5 grams per centimeters cubed, you were way off, so you would have very low accuracy. If you got around 1 gram per centimeter cubed, you would have high accuracy because you're around the true value. And the true values are the set values that scientists have come up with. Precision is all about repetitively getting the same value every time. So if you did that lab and every single time you did 5 grams per centimeters cubed, and that's what you got every single time, you would be precise but not accurate. So the analogy that's used commonly throughout any chemistry classroom that you're in is a bullseye effect. So the bullseye, the center, is your true value. The dots are the different times that you've come up with that measurement. So I want you to take a second, pause the video, and come up whether it is high accuracy, low accuracy, good precision, bad precision for each of these three bullseyes. So if you look at this set of values, they're all clustered together, but they're not near the center of the bullseye. So you should have gotten that it's very good precision because they're all clustered together, but it has low accuracy because it's not around the true value. Then the second bullseye, they're clustered and they're also in the center, so it's going to be good precision and high accuracy. Then the last one, they're not clustered together, and also the average is not in the center. So this is where we have both poor and low precision and accuracy. Now, we're going to talk more about these two words, but to give you a brief overview, significant figures represent precision of a measurement. So if a student weighs a 20 gram weight, like it's written on that weight that it's 20 grams, and it gets 4 different measurements based on the instrument that's used, you get 19.9, 19.94, and so forth. So as you're going, what is changing? Here you have 1 decimal place, 2, 3, 4. So sig figs, which we have 2 whole videos on this, the sig figs are the number of numbers in that number. So 19.9 has 3, 19.94 has 4, and so forth. So the number that's the most significant is going to be 19.9354. 51 is the most precise because it has the most numbers in it. It has the most decimal places. So the more sig figs, the more precise that measurement is. Now, recording sig figs. We're going to do a measurement lab where you have to find measurements of different devices, whether it's the length of it, the mass, and so forth. So you're going to have to be able to tell me what that measurement is based on the tool that you're using. So for measuring the length of the paper clip, we would need a ruler. Okay? So sig figs in a measurement include the known digits plus 1 final estimated digit. So based on this ruler in this video, everybody should be able to tell that it is at least 2 centimeters because it goes past the 2 centimeter mark. So you know for a fact that it's 2 centimeters. Then the little lines between the 2 and the 3, there are 10 or 9 little lines, so that means they're divided by a tenth. So if you look, you know for a fact that it's at least 2.2. Okay, so you know for a fact it's at least 2.2. Then, that's the only thing that you know for a fact are those 2 numbers. Then, the most common mistake is for students to put that it is, oh, just kidding. Sorry, is at least 2.3. I wasn't looking at it good enough, I guess. It's kind of blurry up here. So it's at least 2.3. Sorry. So we know for a fact it's 2.3. Now, most students would put 2.3 or 2.2, whichever one they thought was closest. But your measurement is not correct because you're not recording to the correct number of sig figs. You have to go to that unknown digit, and so you have to base it off of where it falls between these two lines, and it's about halfway there, so 2.34. Now you could have a different number here and be wrong, and still be right because it's an estimated digit. Then, the last thing for this part is we talked about precision being the number of sig figs. Accuracy is based on an actual formula. So accuracy of a measurement can be determined by calculating the percent error. This formula is not given to you. You have to memorize it. So it's accepted minus experimental divided by accepted times 100. These lines here are your absolute value. So the accepted value is the one that's known in the books. It's the one that's in the reference table or in some sort of book somewhere. Scientists believe it to be true. The experimental is the one that you find during the experiment or somebody has found during the experiment. Divided by accepted times 100. Now, since you have these absolute value signs, your answer should never be negative. Now, there's no absolute value symbol on the calculator, so you just have to know that it's always going to be a positive answer. Okay, so, for example, a student determines the density of a substance to be 1.40 grams per milliliter. Find the percent error if the accepted value of the density is 1.36 grams per milliliter. So the students, the thing that they get wrong the most is figuring out what's the accepted and what's the experimental. So it says a student determines the density to be this. So the 1.40 is the experimental value. It says the accepted value of the density is 1.36. So then when you plug it in, and you need to be copying this down and following through with this so you're able to look back at your notes and do these kind of problems. So the 1.36 would be your accepted minus 1.40. Remember, absolute value of that divided by 1.36 times 100. When you plug this in, your answer should be 2.94%.